This trolley, it's running all by itself. There are no expensive controllers, no complicated software. Just this, an Arduino, and a few simple parts. You really don't need a ton of fancy gear or years of experience to get your model railroad automated, and I'm going to prove it. We're going to take this Arduino and some basic sensors to build this exact hands-free shuttle. And we'll do it right here in less time than it takes to have a lunch break. So stick around. All right, let's talk about the dream. For so many of us in the hobby, it's watching our trains run on their own, bringing the whole layout to life. But then you start looking into it and you just hit a wall. You see these crazy wiring diagrams, super expensive systems, and code that looks like a foreign language. It's enough to make you think automation is only for experts with really deep pockets. Well, I'm here to tell you that that's just not true. The goal today is simple. We're going to create a reliable point-to-point shuttle that starts and stops at each end and reverses automatically, running all day long with zero help from us. And we're going to do it in about 30 minutes with inexpensive, off-the-shelf parts anyone can get. This is a perfect project for a small shelf layout, a display track, or even just your first step into the awesome world of model railroad automation. And this is all DC based. And so you don't need any special DCC gear. We're going to break this down into 3 parts: the parts list, the wiring, and the code. I'll explain everything as we go. By the end of this, you'll have a working shuttle and, more importantly, the confidence to try even bigger projects. First up, let's run through the components you'll need. I put links for everything down in the description to make it super easy for you. The brain of the whole operations is an Arduino board. I'm using an Arduino Uno, but a Nano works just as well, and it's even smaller. This is the little computer that's going to be making all the decisions for us once we load our program, or sketch, onto it. Next, we need a way to actually control the trolley's motor. For that, we've got this L298N motor driver module. Think of this as the throttle and the reverse switch all in one. The Arduino tells the motor driver when to go, when to stop, and which way to go. It's an H-bridge driver, which is a fancy way of saying it's designed to flip the voltage priority to a motor, which is exactly how you reverse a DC locomotive. It can handle more than enough power for our little N-scale engine. To tell the Arduino where the trolley is, we need some sensors. We're going to use 2 simple infrared or IR reflective sensor. Each one has a little LED that shoots out an invisible beam of light, and another sensor that looks for that light to bounce back. When the trolley passes, the IR light reflects off of it, and the sensor tells the Arduino, "Hey, the trolley's here." So we'll just put one at each end of the track to mark our stops. Of course, we'll need some hookup wires. I have an assortment of jumper wires, male to male, female to female, and some male to females. And it goes without saying, you'll need a 12-volt DC power supply. I have this connector which allows me to connect the transformer to the electronics as well. A USB cable to program the Arduino from your computer. I use these Wagyu connectors when wiring the main layout, and I really like them. They'll make splicing the common wires together a snap. The breadboard is awesome because it lets you connect everything without any soldering, which is perfect for a quick project like this. A Kato power connector will get power to the track, and of course some Unitrack to run the trolley on. That's it. That's everything you need. Okay, with all our parts in front of us, it's time to wire everything up. This might look a little intimidating, but trust me, it's just connecting the dots. And make sure the power is off for everything while we do this. First up, the sensors. They've got 3 pins, VCC for power, GND for ground, and out for the signal that goes to the Arduino. We can connect them right from the Arduino itself. Connect the VCC pin on both sensors to the 5-volt pin on the Arduino, then connect the ground pin on both sensors to one of the Arduino's ground pins. I'm using a common bus on my breadboard to accomplish both these tasks, but you can tie the grounds together and the 5 volts together with the Wagyu connectors, and you don't have to use the breadboard. Now for the signal pins. This is how the Arduino reads the sensors. Let's connect the out pin from our west station sensor, pin number 2, and the sensor for the east station to pin number 3. Next up, the motor driver. This L298 module has a few important spots. You've got screw terminals for your power in and the motor out. So go ahead and connect your track power supply, like the 12-volt DC brick, to the plus 12V terminal. The ground wires will connect later, but for now, let's just connect a male-to-male jumper wire in that ground slot. Again, I'm using the Kato power feeders to supply power to the track. I decided to snip off the Kato plug, and then I can just directly feed the wires into the motor driver. The out 1 and out 2 terminals to the 2 feeder wires for the track. Don't worry about which wire goes where now. If the trolley goes in the wrong direction later, we can just flip these 2 wires and we'll be all set. Now let's connect the brain to the muscle. The LN298N has an enable pin labeled as ENA and 2 output pins, in 1 and in 2. The ENA is basically our speed control. One very important step before we start connecting pins. See this little jumper here on the motor driver near the power terminals? Since we're using a track power supply that is 12 volts, you need to pull that jumper off. The jumper enables an onboard regulator that we don't need, and leaving it on could damage the board. With the jumper removed, any voltage over 5 volts will now be regulated down to 5 volts and available on the 5-volt connector on the power strip. We'll use that later to power the Arduino. We can use a special signal from the Arduino called PWM, or pulse width modulation, to set the speed. But for now, let's just get it running. Connect the ENA pin to a PWM capable pin on the Arduino, like pin number 10. Note, any pin with the tilde is a PMW capable pin on the Arduino board. Then connect in 1 and in 2 to any of the digital pins. I'm using pins 8 and 9. Remember, we need to tie the motor driver and the Arduino ground wires together. So I used the Wago connector to accomplish this task. But you could connect both wires directly to the terminal. Just make sure they're both very secure or you'll have a ground fault. Lastly, we use 2 male-male jumpers to connect the ground to the Wago connector as well as to the ground pin on the Arduino. Here's a pro tip. Make sure all the grounds in your circuit are tied together is super important. It prevents all kinds of weird, unpredictable problems. We also need to get power to the Arduino, so we'll use jumpers to go from the plus 5 volt on the motor driver to the Arduino's board's V-in terminal. And that's it for the wiring. Seriously, that's it. We have sensors that see the trolley, a driver that can power the track, and an Arduino to run the whole show. All right, hardware's done. Time to give it a brain. We need to write the Arduino sketch that holds all the logic for our trolley. Don't worry, you don't need to be a coder. I'm not. I'm giving you the full code to download, but I want to walk you through it so you can actually get what makes it work. The code basically does 3 things. It defines our pins, it runs a quick setup routine, and then it just repeats that main logic over and over and over. I've also set up 3 simple functions that avoid cut and paste errors and a simple debounce to keep things running smoothly. At the very top, we declare variables. This is just where we give nicknames to the pins we're using. So we'll create a variable called IR_west and tell the code that it's on pin 2, and IR_east, we'll set that to pin number 3. And we'll do the same for our motor driver pins, remembering that ENA needs to be on a PWM pin, and we set that to 10. I've also set up 2 additional integer variables to control speed and stop delay. Having these global variables makes changing the stop time and the trolley speed much easier. We don't have to hunt and replace every call. We just modify those values of these integers and it changes it whenever the code might use them. I made a variable to keep track of the trolley's direction. I use a bool declaration, which is to say this variable will be a boolean, which can only hold 2 values, a value of true or a value of false, and its initial value is set to true, i.e. the trolley is running forward. Next is the setup function. This part only runs once when you power up the Arduino. Here, we tell the Arduino which pins are inputs and which pins are outputs. The sensor pins are inputs, since the Arduino is listening to them. The motor pins are output, since the Arduino is talking to them. We'll also go ahead and tell the trolley to start moving right away, right here in the setup. So it gets going as soon as we turn it on. This is done by calling the function move forward. This function basically starts the flow of current to the track and tells the program the trolley is running forward. The delay function is set to half a second, which keeps the IR sensors from triggering an additional reverse while it's still at station. It's crude, but it works. Now for the real heart of the program, the loop function. This is where the magic happens. The code here just runs on repeat, thousands of times a second. Inside the loop, the first thing we need to do is check on our sensors using a digital read command. The sensors send a low signal when it sees the trolley, so that's what we're looking for. And we also have to check if the trolley is moving forward. The logic is just a couple of if statements. The first one basically asks if IR sensor east is triggered, i.e. it sees the trolley, and the trolley is moving forward. Both of these functions are true. It's time to run our reverse train function. The other condition is that the trolley is running in the opposite direction and IR west is triggered. Using the explanation symbol ahead of the Boolean variable changes it from current condition to the opposite. So in this case, we only call the function if the train is running towards the west sensor. Reverse train function works like this. Firstly, we tell the motor to stop by setting the enable pin to 0, cutting power to the track. Then we use our delay command to make the trolley wait for however many microseconds we've assigned to stop delay. Currently, this is set at 1,000 microseconds or 1 second. After that pause, we check the value of the train forwards variable. And if it's true, we call the function move backwards. This function sets in1 to low and in2 to high, updates the speed on the ENA, and sets the direction forward to false. If the initial value of train forward is false, then the function move forward is called, which sets IN1 to high and IN2 to low. The function also reestablishes the motor speed on the ENA pin and sets the direction forward back to true. Then the loop starts all over again. Using these function calls keeps the code clean and easy to debug. It also keeps the loop very short, just 2 statements. That's the entire logic. It's a simple loop of checking sensors and reacting. The trolley just keeps doing its thing until a sensor tells it to change what it's doing. All right, the moment of truth. Wiring's done. Code's ready. I'm plugging the Arduino into my computer to upload the sketch. Inside the Arduino IDE software, I just pick the right board and output port and click upload. Done. The brain is officially programmed. Now let's put the trolley on the track, somewhere in the middle. I'll turn on the track power, and so there it is. And about the time it takes to make and eat a sandwich, we built a fully automated, hands-free shuttle for a model railroad. We've proved to you don't need to drop hundreds of dollars to become a computer scientist to bring your layout to life. All it takes is an Arduino, a few basic parts, and just a little bit of curiosity. What we built today is just really the beginning. From here, you could add more sensors for more stops. You could control turnouts to have the train switch tracks. You could even add working signals. The possibilities are pretty much endless. And it all starts with a simple project just like this one. If this build inspires you and you want to see more projects to take the mystery out of tech and our hobby, make sure you subscribe and hit the bell so that you don't miss what's next. If you have any questions or an idea for another project, drop in the comments below. Thanks for watching and keep an eye out for the next steps in this project. For now, go build something. And I need to go eat lunch.